Hi, thanks for coming. This talk is called Lies, Damn Lies, and Metrics. It's about the ways metrics can be tricky, can omit vital information, and can sometimes even actively mislead you about what it is that you actually need to know. Before we get into that, let me introduce myself real briefly. My name's André Arko. I'm on pretty much all the internet things as indirect. I work at Cloud City Development doing consulting for startups that do web apps, and this is kind of like a bundle of things that I have learned because we were very sad at work about discovering them. So hopefully you can learn from all of the horrible things that have happened to me, and then maybe they won't happen to you. If if that's something that your work could use help with, that is also a thing that I do professionally. So maybe talk to me later. The other thing that I do is work on Bundler, the Ruby language dependency manager, which provides like a whole new set of failure modes for computers. I'm not going to go really deeply into those, but I definitely have some interesting stories if you want to hear about them after the talk. So let's start with metrics. I guess people who make web apps in general are kind of usually pretty good about like at least having metrics, which is like a big step up from where people who make web apps were when I started in the field in like the early 2000s. And drop-in services like New Relic or like there's a whole cottage industry now of like, we do all the metrics, you just add this one line to your thing and we built a plugin for your programming language and now you have all these metrics. Here, look at this dashboard. Isn't it great? And that is really cool. Don't get me wrong, it is way better. That is way better than the prior state where no one actually had any idea of what was happening at any time. You could like tail the web server log and be like, I think a thing happened. This is an improvement. And without any metrics, like I was just saying, like your information is basically limited to is it up? Did it work? Could I see it? I can't. So that's really cool. And the first time that like how metrics are really useful to kind of like peer deeply into the black box of production really hit home was at GitHub's first code conference back in 2009. Coda Hale gave a really great talk called Metrics Everywhere. And if this talk interests you, I totally encourage you to find the video on YouTube and check out that talk as well. But his ultimate point was that the reason that we write applications that have customers, at least, is to deliver business value. And the only way to know if you're delivering business value is to set up metrics so that you can measure it. And at least for me personally in 2009, that was like, wow, I never actually realized that succinctly before. That's a really good point. So at this point, I'm going to go out on a limb and say, you're like, yeah, metrics, I know, they're good. So this is the point where I try and convince you that you want to listen to the rest of the talk, because it's great that metrics give you visibility into more than zero things. The problem is the way human brains work, having visibility into more than zero things means that you are now convinced that you have visibility into all of the things. And the way metrics work, you don't. And so not having total visibility means that you're going to be really surprised and really sad later when you figure out that the thing that you weren't paying any attention to because you didn't have a metric for it was actually the problem. So I'm going to talk about some specific ways that metrics mislead you and mean that you think you have a much fuller picture than you actually do, and then I'm going to give some like concrete examples of things that most people don't realize are potentially screwing them over, but how would they know? They've never looked at them. So the biggest, and I don't know how to, if I could like, in retrospect, I should have made this like flash and blink and have a rainbow. Like the biggest problem with metrics today is averages. When you have a lot of metric information, the easiest, like human beings can't comprehend like thousands and thousands of actual numbers. And so what do? Well, you have to distill it down to some kind of like aggregate And well, what's the easiest aggregate? Well, averages is the easiest aggregate. You add them all together and then you divide them, and you don't even need to like keep track of any of the individual pieces of information. You just kind of like throw them all in a bucket and you're like, here's the average. So, for example, New Relic, not to like, and historically this was much worse. New Relic as a drop-in metrics thing, once upon a time, said, here are all your averages, that's all the information we have a great day. They've improved. They actually spent 5 years building a like super scary, impressive, high-velocity data store that keeps all of the raw data from all of your metrics, and that you can query with like any aggregate that you want, or any time span that you want, or any conditions that you want. But the default view, and this kind of pisses me off, is still a giant graph of all of the averages. And the problem with averages is that brains and averages don't go together well. So brains are really good at finding patterns. This is how brains see Jesus in toast. This is how you see an average and you think, aha, I know what is happening. So when you see an average, your brain, without any other like specific input, automatically says, aha, this is an average and a standard distribution. So this is a normal distribution or a standard distribution, often called a bell curve. And this is what happens when every value is random. And that's like a very cool thing. But the problem is the metrics that you're collecting aren't actually random. Like okay, I take that back. If you run random.org, your metrics should look like this. But if you don't, then you're not collecting random data, and when you see an average and your brain automatically extrapolates this bell curve, you are actively misinforming yourself about what is happening, and that's really problematic. So a giant feature of this bell curve is that 70% of the values, like of the total number of values that were used to produce this bell curve, are within one standard deviation of the middle, the average. And so brains, when they see average numbers, think, oh, that's what most of the values looked like, that number. And in real life, not so much. Here is a graph containing made-up results from real-life data based on lots and lots of real-life data that I have seen and worked with. You're kind of mostly grouped around two numbers. It's totally uneven. So to make it easier to see how averages can wildly mislead you, let's like stack a bunch of these together and take a look. So here is a data, like here are all of the data points from a whole bunch of metrics. And each line with all the ups and downs is the result of collecting a metric at, over a while. And the higher each peak is, the more times it was at that value, right? So we collect metrics for 10 minutes, and if you got it 25 times, it'll be a higher peak than if you got it once. The small black lines, which, oh yeah, you can see them, they represent the average value for that particular metric. So let me line up all the black marks for you that represent the average for each one of these individual separate metrics. So not only do none of these collected metrics look anything even vaguely like a bell curve, a bunch of them have basically 0 data points at the average. And so you can see an average number and think, I know what's happening. And then you look at the actual data underlying that average and you're like, wait a second. I collected that number that I've been looking at and thinking gave me like a representative view of what was happening. That never actually happened in real life, not even once. And so this is the overall problem with averages. Like, unless your metrics fall into a standard distribution, and really, unless you're running a randomness server, your metrics are never going to fall into a standard distribution. Your averages are going to actively mislead not just you, but anyone else who sees those averages. So while averages changing over time can tip you off that something is going wrong, they can't tell you what changed, and they can't tell you how it changed. And those are usually the two pieces of information that you need to actually do something useful about it. And so averages are, I guess, being as generous to averages as I possibly can, they'll at least tell you that something happened. Everything else is now up to you. So let's look at an example of how that can happen. So here is a graph. It's not a real graph, but it's very representative of many graphs that I have known. And based on this line, which is an average, there could be many, many events happening kind of in that lowish range between, you know, maybe 30 and 150. Or there could be 80% of the events happening in the 0 to 10 range, and maybe 10% of the events happening somewhere off the top of the scale of the graph. You have no idea. It's an average. Cool. So the first way to get useful information out of a metric that actually tells you something that did in fact happen in real life is the median. So to review basic math real quickly, the average, also called the mean, is every value added together and then divided by the number of values. The actual average, as a result, might not have ever occurred in real life. The median value, on the other hand, is the value that was higher than half of the values that you collected and lower than half of the values that you collected. So at least you are getting a real-life value that is smack dab in the middle of everything that you saw happen. So here's the median. As you can see from the purple line, well, we've already started to learn something that the average couldn't possibly have told us. At least half of the values that we're collecting in this situation are actually very, very low. So in that spot where the average jumped up really, really high, like it tripled from what we were seeing earlier, the median didn't change appreciably. And so what that tells us is that probably a few values went up a lot, and most of the values didn't go up really much at all. So once you're starting to see what's happening kind of in the middle of your data set, you can start graphing more things that tell you even more information about what's going on. Graph the 95th percentile. So the 95th percentile is the number that is higher than 95% of the values that you collected and lower than 5% of the values that you collected. And here you can see that the slowest, or the values that we collected with the highest numbers, the 5% with the highest values are dramatically higher, more than 10 times higher than the median. So continuing that trend, it's also really valuable to graph the 99th percentile because in most of the scales that most web developers deal with, 1% is probably the magnitude that you actually care about. Like, this is happening often enough that it's a problem and we should deal with it. I guess as Julia Evans mentioned during her talk about kernel debugging, if you have a huge number of events happening, suddenly smaller and smaller and smaller percentiles become relevant to you. Because if you're Twitter and you have 1 billion tweets happen a day, I don't actually know if that happens, I'm just making up a number, but if 1 billion tweets happen a day, then your slowest 0.0001% of requests happen literally 1 million times a day. And so maybe that is the number that you actually care about, because those million users are going to be really unhappy with how slow their requests are. And so I actually know from chatting with some people who work at Twitter that they don't bother to graph 50 or 95 or 99 or any number even vaguely like that. They start at 99.9 and they go up to 99 point, I think, 49s, because that's the number that gives them a small enough number of events that they actually care about how many people that's impacting. So notice that this graph has just had to increase in scale by 4 times to accommodate the 99th percentile. And now we have learned why the average went all weird. 1% of requests got incredibly slow while everything else continued more or less exactly the same as it was before, and the average went up, tripled for that time span. So now, when we're trying to work through this and resolve it and keep it from happening again, we know that what we want to look for is a very small number of specific requests that dramatically slowed down from what they were before, or new requests that are very slow that weren't being made except in this brief time span. And so this is a pretty clear example of the way where an average doesn't actually help you debug or fix a problem, but seeing the percentiles actually gives you a pretty strong lead on what you should be looking for and what you should be expecting to have to do to keep that from happening in the future. So another common problem that happens with averages is aggregation. And aggregation is, of course, a fancy way to say that you're averaging across multiple servers. And so if you're running a typical web application, you're going to have more than one machine, because one machine isn't good enough for most web applications. And so, for example, again, if you use some drop-in service that collects metrics from all of those machines, you're probably going to see one graph. And that's an average. So this is, for a change, actually real-life data that I collected from some servers that I run for the Ruby Dependency Manager's server-side API that gets called anytime someone tries to install some Ruby libraries. As you can see, the number of milliseconds being measured by this metric started around 2, jumped up to over 5, and then eventually kind of recovered to back around 2. So what does it actually mean? Well, we don't actually know because it's an average. But you can break out the graph, and instead of seeing a single aggregate, you can see an overlay of all the individual things on top of one another. And here's the breakout graph of that same data. So A, notice that the scale has actually increased by 10x from the graph we were looking at before. And notice that out of these 15-ish servers, only one of them actually suddenly got slow. And this breakout graph let me see which specific server out of 15 suddenly got super slow, actively nuke that server, and automatically start a new instance, and then it recovered and everything was fine. Without this breakout graph, I had no idea what was happening. It got really slow, I don't know. And with this breakout graph, it was like, oh, this one specific server is problematic, there, problem solved. So one of the things that I'm trying to get across is that visualizing your data is basically the only way to get anything useful from it into your brain. Human beings don't deal well with gigantic streams of numbers, even if they do have patterns in them, but humans deal really well with pictures. But having said that, you really need to break things out, and you really need to, if you can't break it out, see the contents of that data rather than just the averages. So one last illustration to try and really drive this point home before I move on. Here are 4 different data sets. As you can see, the X and Y values are wildly varying between each of these 4 data sets. You can see very, very quickly just by looking at the actual data set, oh, these are 4 completely different things. They're basically unrelated. But if all you had access to was aggregate information about this data set, it's a completely different story. So, for example, the average of X in that graph is 9. The average of X in that graph is 9. The average of X in that graph is 9. And the average of X in that graph is 9. It gets much, much worse, actually. You're like, oh, I'll be clever. I'll have more aggregates, and they will show the differences between my data sets. Well, the average of Y, also the same on every one of those data sets. Wait, it gets even worse. Every one of these 4 data sets, which once you can see the data, they're very, very different, has the same average of X, average of Y, variance of X, variance of Y, correlation of X and Y, and the same linear regression. That was a very long way of trying to say, please don't trust aggregate information about multiple data sets and do whatever you can to actually draw the data that you have into a graph that you can look at, because those are just four completely different, unrelated things. One last thing, aggregate alerts are similarly horrifying, because if you have an alert that only goes off once you have more dead servers than you have alive servers, it's not actually very helpful. So don't use the average of status checks to do anything. Use individual status checks and alert on the first problem rather than an average problem, and you'll probably be much better off. I recognize that most of you are probably fine on that front, but I've run into enough places where it turns out that the alerts were actually based on some sort of aggregate average measure that I just want to call that out, because check. If it's not, I'm really proud of you. If it is, you have just saved yourself a really bad time down the road. Speaking of servers, I have a couple things to say about servers and how they can also provide you with some unexpected misleading results, especially in metrics, and then I'll wrap up. So, you pay for your servers. They are theoretically hardware eventually, right? You pay someone who pays someone who pays someone who has hardware, something like that. But even if you bought the hardware yourself and you racked it yourself and you put software on it yourself, when you're not in the data center and it's like serving requests, you don't really know what's happening inside those servers. And so I'm going to call out a few things that most people don't know that they don't know about what's happening in those servers, and we'll talk about ways that those can be problematic. So here's a really interesting / weird example. Whether you use whatever language you use, right? Web applications are usually written, I say this statistically, not because I think any of you are necessarily doing it, but statistically, web applications are written in a scripting language like Ruby, Python, Node, Go, Perl, or maybe in Java, statistically. But all of those languages contain a runtime. And the issue with runtimes is that they do things that you didn't write code for, like, for example, garbage collection. That's really cool, don't get me wrong. I like having my garbage collected. But that means that there are times when your program is running when your code is not. And most people don't, until this has really punched them in the face as a problem, think about the fact that that is necessarily true. So if your program isn't running while your program is running, how do you tell? And some runtimes provide their own statistics. The JVM is probably the best in this regard. You can like actually ask it what it did, and it'll tell you at least how long it took. Other languages may not provide useful things. For example, the Ruby interpreter didn't tell you how much time it spent doing garbage collection until about 2 years ago, and I've been doing this for about 10 years. And actually, to make things even worse, there was, for maybe 7 years, there was a garbage collection profiler built into Ruby, and it contained a memory leak. So you couldn't use it, which was amazing. And you know, now that I've called out garbage collection really specifically, don't let that fool you. The runtime will stop running your code and run its own code for reasons that aren't necessarily garbage collection, right? There's a lot of bookkeeping to do. There's a lot of things that happen that you didn't explicitly write code for that are built into the language or the VM or the whatever it is that you're running your code inside. So, as we've established, unless you're like writing compiled things and running assembly to serve your web requests, in which case I'm very sorry, you have runtime lag, but how much do you have, right? If you can't directly instrument this, how do you even find out? So I learned a very cool trick from Larry Marburger, who maybe even is here, which is run some code inside, like write your own code that says, hey, I would like to pause for exactly 1 second, and then I would like to keep going. And if you check a very precise system clock, both before and after you ask to wait for 1 second, you can know how much time your 1 second wait didn't spend running during that 1 second. And so that graph that I showed earlier with the aggregate that ran on each individual web server, it was actually how many milliseconds longer than 1 second it takes to call sleep 1. And if you run how many milliseconds does it take to call sleep 1 in a loop, suddenly you know how much time your program is spending not running while this process is executing. Turns out that's really, really helpful when suddenly, for no particularly apparent reason, one of the servers starts spending a significant percentage of the time not actually running your code. And you're like, why are the RPMs down so much? I don't understand. And then scaling backwards from your language runtime, guess what? The language runtime is running inside another runtime. So you're running on a processor, except your processor probably isn't, in some sense, a real processor, because if you use servers today on the internet, chances are really, really high that you're virtualized or containerized inside virtualized, inside containerized, inside I don't know. Anyway, so virtual machines are exactly like runtimes. Your code may or may not be running at any given time. And the only way to really find out what's happening is to examine external factors and be like, hey, that isn't what would have happened if my code had been running the whole time that the VM was running. So, unfortunately, I don't have a cool trick to let you check for VM lag, because if the VM pauses, that will go into the metric that I just talked about, where you get runtime lag. And so if you care about a specific contended resource in your virtual machine, you're going to have to figure out yourself exactly what contended resource that is. But at a very broad entire VM level, I have heard rumors that Netflix checks for this in a pretty cool way, where they spin up a VM and then throw a benchmark suite at it. And if the instance meets their benchmark baseline, then they say cool, and they start putting production software on it. And if the instance doesn't meet their baseline benchmark, they say, nope, never mind, Amazon, give me a new one of those. And then they try again. And as cool as that is, because research indicates that provisioning, for example, a single Amazon instance in a single size tier can give you up to, I think the highest that they saw was a 5x difference in performance at the same price point. And so if you're not looking into how performant your instances are after you ask Amazon for them, well, maybe you're overpaying by 5x. I don't know. That's a little terrifying. And then it gets even worse, because, of course, the performance of a single instance can vary wildly over time as new neighbors on the same physical hardware come and go. So do you re-benchmark those machines? Did you just find out that last week you were suddenly having really a lot of trouble serving your usual traffic with your usual number of machines? This is also a problem. I don't have a really good solution for that either, other than to say keep a really close eye on how many requests per second, for example, your servers are able to sustain usually, and if that number changes, look pretty hard at that and maybe think about swapping out the instance that it's running on. So, again, going back to do you know what you care about? Depending on what you're running on that instance, you may care deeply about CPU contention on the same physical hardware, but not care at all about, say, disk contention. You may be running memcached and care deeply about RAM contention. Good luck figuring out how to check for that. That's really hard. But that may be what you care about, and you may not care about CPU contention because memcached in general doesn't really use much CPU. Or you might be running a database, in which case you care about all the contentions. Right? Databases are highly optimized to use all the CPU, all the memory, all the disk, and all the I/O. But that means that if you run anything else on the same physical hardware, the database is no longer optimized for that situation, and so you can see wildly varying situations. So I highly recommend that you like look at this and try and figure out what the variance is between instances and how to keep an eye on the specific things that you care about, because they can just drop out from under you without any warning and without anyone telling you about it. And then one last thing. Outside the runtime, outside the virtual machine, there's one more thing that could be destroying your real-world performance without any metrics or instrumentation on it, and that is routing. So when I say routing, I mean the piece of infrastructure that takes requests from the outside world and makes sure that they arrive at your actual servers, and then takes the responses from your actual servers and makes sure that they arrive back in the real world. So how does routing work? It's totally possible that you work professionally as a web dev for many years and have literally never thought about this ever, because this is what your world looks like. And that is, don't get me wrong, that's fine. Like, I have no expectation that you would have thought about this if you haven't had to figure out why, God, why this works perfectly fine and this doesn't. So in production, you clearly have some single point of entry, wherever matches up with your domain, and then is like, oh, well, here's a server, here's an app process running on that server, here's a thread running on that server, here's a something. It breaks down into smaller and smaller individual pieces until you say, aha, here's the response, and then it has to like pass back up through that entire hierarchy of things. And so if you're on Heroku just like takes care of this. If you're on Amazon, they offer their own EC2 or Amazon cloud routing things, which is cool. Maybe you set up your own HA proxy or your own Nginx, or your in some startups I've known, your own HA proxy that talks to Nginx that talks to HA proxy. It's amazing. But, and this is the question that no one really seems to know the answer to, how slow is it? So I've asked this question of, at this point, probably closing in on 1,000 people. Raise your hand if you know, or at least you know where to look up, exactly how much time your routing layer on your web application takes. I am so proud of you all. I have given this talk at DevOps conferences, I've given this talk at Ruby developer conferences, and so far my grand total was 1 person. And this was like 15 people. Like, this is amazing. This is more than I could have hoped for. I'm super proud of everyone here. You're making me tear up a little bit. So the next question that you immediately want to know, once you know how long it takes, is, does it back up? And so if your load balancer does simple round robin, chances are, there's no chances. If your load balancer does simple round robin, the answer is yes. You should find out how badly. It could be not that bad. It could be very, very bad, and your users are seeing 30-second delays or timeouts while your application instrumentation, all those cool numbers that New Relic gives you for free, say that everything is great. So once you know that routing exists, here's what you can do to at least keep an eye on it, and that is find out what your real-life request time is, right? Like, New Relic says response time, but that doesn't actually mean how long it takes for a request to arrive, to be processed, and to be returned. That only tells you how much time it spent inside your actual like web application, parsing the headers and concatenating a giant string to send back. So it's really useful to see how slow things are inside the code that you have control over, but it doesn't actually give you a good idea of what your users are experiencing, because what your users are experiencing includes gigantic network hops. It includes a round-robin router that might be backing up hundreds of requests before the New Relic timer even starts ticking. You might have to wait for 100 requests to be served because routers are terrible. And finally, it doesn't account for like real-life transit times, because unfortunately, even electrons have measurable time that they take to get to places. So the only way to know how long a request actually takes to get across your entire infrastructure is to set something up that makes requests across your entire infrastructure and then tells you how long they took. There are a couple of services that do this. Pingdom has finally expanded into doing this from all around the world. RunScope does this. There's another service called Thousand Eyes that also does this. And like their entire reason for existence is we go to data centers all around the world and we hit your entire infrastructure top to bottom, front to back, I don't know, one of those things. And then we tell you how long that actually took because that's the number that your users are actually going to care about. So the reason, of course, that you should care about this a lot is that the number that you see in how long something took inside your web application server is going to be much, 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 much lower than whatever you see coming back from this real-world metric. And for example, Amazon said in 2006 that 100 milliseconds slower in their entire checkout process, which is like 6 steps, 100 milliseconds of slowness across that entire process dropped their overall revenue by 1%. And when you're Amazon, 1% is like a lot of zeros. So in the end, metrics are actually pretty good, but you need to know what you're measuring and you need to know how what you're measuring impacts the things that you care about in real life from a business perspective. That's it.